Okay, well, thank you everybody for joining us today in our first webinar for the next recruitment cycle for February 2021. So today's webinar, as you can see from the screen, is our webinar on electrical power systems engineering, where I'm delighted to be joined by course director James Brooks, who I'll hand over to in a moment. But today's theme is around industry trends. And also James will take us through a number of slides to look at our course and how it relates to the industry. So for those of you that have, I guess, never spoken to me or seen me before, my name is Craig Donaldson and I'm the course director. Sorry, James, course advisor. So
Right.
my role is not James's. So my role is to help you guys who are considering applying for the course, and you might have a number of questions relating to the application form, your entry requirements, or the course fees. And it's my job to help you with those questions and guide you through the application process, so you could submit your application for James to review. So today I'm here to support you guys in terms of firing questions through that I can pitch to James at the end of the presentation. So you'll notice that there is a chat icon at the bottom of your screen. So please do feel free to send your questions through, and I will obviously pitch these to James at the end. I'll just check. It looks like we have got a couple of hands raised, James, just before I do hand over to you. I was just wanting to make sure that people could hear me and hear
It
you.
looks like someone can't hear you. So
Yeah,
if other people can hear us okay, can you just message into the chat?
yeah.
Um,
So Dean has just said he
and
cannot
said he
hear us.
can't. Can other people hear us okay?
Yeah, this is okay. So there, yeah.
I'm surprised that
Yeah.
it should be working because I can hear you and we're obviously
Yeah.
not based at the same place.
Sure. Yeah. So thanks, Oliver. I think he can hear. I would just suggest just checking your audio settings on your laptop. It does look like most can hear you and me, James.
Okay.
So yeah, just on that note, before I do hand over to James, please just do check that your microphone and camera are off so it doesn't interfere with James's presentation. And as I mentioned before, please just send your questions through via the chat. Okay, I think that's enough from me, James, and I'll let you take over.
Excellent. Yeah, thanks, Craig. And thank you for everyone to coming along and listening to this. So I was going to have a little chat about some of the industry trends that I've been finding interesting, and then a bit of a conversation about the course. But as Craig said, I am the course director, so I'm kind of responsible for the academic content of the course as a whole, or at least I help pull it together. There's quite a large team involved. I'm a senior lecturer in electrical engineering within the Faculty of Science and Engineering, but I'm also the academic lead for pedagogy across all of science and engineering. So I have a real interest in improving the quality of education, improving the quality of taught content, and hopefully that comes through in the course that I've put together, or I've put together with a number of other colleagues. And back when I did my PhD, which is a while ago now, I was looking at kind of what happens if we have a large number of generators that you can't schedule, such as wind power or solar, and how do you quantify the risks with that renewable power generation. So yeah, that was back with what I did. And then just about the course very broadly, or about the way I think about what electrical power systems is. You can take electrical engineering into low power and high power. You've got the electronic side and the electrical side. We're obviously the electrical side. But within that, you can then split it into machines and drives and systems. And we're the systems side. We're the, okay, someone generates some electricity. How do you get it reliably to the people who want to use it? So that's what I call the systems view. Each generation, transmission, distribution, and consumption. And that incorporates, what are the components? What's in a substation? How do we analyze a system as a whole? How do we analyze parts of a system? How is it operated? How is it managed? Particularly, if you've got a suite of assets such as transformers, switchgear, etc., that are exposed to the elements over decades. How do you kind of look after those? How do you ensure that there is reliable operation? How do you protect against faults? What's the new innovations? What's changing? How do you investigate those yourselves? Because it's too broad a subject to be able to teach you everything that's new and up and coming. So we really try and get the fundamentals of each of the key areas. And then we talk a little bit about how do you investigate the new areas for yourself. So that's what electrical power systems is. In terms of talking about the industry, there were some points, some places that I thought were particularly good to look at. So the European Commission produces quarterly reports. Deloitte's Power and Utilities Outlook I thought was quite good, quite a short one. The IEA does quite regular ones, regular outputs. Our World in Data, particularly for historic things, is very good. It's kind of classifying at a very high level, but it presents it so clearly that it's fantastic. And then I just picked out one example paper talking about what's coming and what's new about power systems as a good example. So all my slides come from one of these. There's nothing particularly new, but it's maybe the juxtaposition of them makes them interesting. And this one, we're just looking at global investment in the power sector. So the energy sector is even bigger because that's considering kind of multi-energy systems. So the fuel that goes into vehicles and transport, the fuel that goes into heating, and also electricity being the sort of three big ones. But this is just the electricity investment. And what you can see is it's measured in the hundreds of billions of dollars. It's a huge industry. At least, last decade was growing rapidly, is possibly stabilizing a bit more now. Although I think this paints a slightly skewed picture. So what you're seeing is quite a lot of the investment is in the networks and in renewable power. The amount in fossil fuels is going down, as you might expect, and nuclear is increasing. But if you just look at that sort of fossil fuels bit and the networks bit, there's a slightly different view. So just looking at the renewable powers, there is a massive increase in the last few years in solar and wind, particularly. There is large increases in some of the others as well, but just the scale of these are just so huge that it's changing what's possible, and it's changing what we thought was going to be possible. And those investments are paying off. If you look at here, so what we've got is the cost, or the relative cost, of building new power plants. And on the right, you've got your traditional power plants, your coal, nuclear, gas, and hydro. And really, there's not much change. You're seeing, if you look at that very last year, so 2018, things are within a couple of % of what they were a decade ago, or maybe there's actually an increase of a small amount. Now, so if you're building traditional plants, not much change. If you're building renewable plants, the more modern ones, the wind power, battery storage, and solar PV, okay, battery storage isn't really a generation source in the same way as the others, but there you're seeing kind of huge reductions in costs, installation costs. And if we look at onshore wind, that's 20% cheaper than it was a decade ago. If we look at battery storage, that's less than half the price that it was a decade ago. And if we're looking at solar panels, solar PV, well, that's slightly more than a fifth of the price, maybe a third of the price. So you're seeing an 80% discount almost. And obviously that means there is an exponential rise in the amount of these that are being installed, which is leading to even more investment, because people are saying, well, okay, this is the future, this is where things are going. But there's a whole load of extra complexities that comes with this. The stuff on the right, you can say, produce this amount of power at this time and be pretty sure it's going to do it. The stuff on the left, you can't tell how much power to produce. You can't open a valve, shovel in more coal, whatever it is. The sun will shine as much as it shines. The wind will blow as much as it blows. And your forecasts will be off by some amount. So I think that's an interesting tie-up between kind of environmental concerns, costs, investment, and the practical engineering aspects that I find really interesting. And this was just showing kind of this just I don't know, exponential decline, massive decline. It's not exponential, huge decline in the cost and installed capacity of solar panels in the world. Obviously, they'd be linked, but to just see such a sharp decline is fantastic. Same if you look at wind energy, there's just this exponential increase in the installed capacity of wind power. Again, something you can't schedule in the same way. And when thinking again about renewable resources, a lot of what kind of comes from renewable resources, it was historically, you look at the really high places with really high usage, and that's okay, they've got access to massive amounts of geothermal or massive amounts of hydropower. But because there's so much solar and wind entering the market now, that this picture is changing over time. And the countries that traditionally relied on fossil fuels maybe have other options and don't need to as much. And I guess with all I've said there, this picture might be a bit surprising. So this one is investments or changes in investments. So rather than how much has been invested, what was the difference between 2015 and 2018? And what you can see is some places, places that sort of historically invested very heavily in solar PV, wind, that the renewables have suddenly decreased their investment in that, probably because we're seeing we're sort of reaping those benefits now in those countries, whereas somewhere like India is investing much more heavily in that now. But you can see the US and China are now having to upgrade and invest their networks to manage that. And that's why I think power systems is such an interesting topic, because yes, you can come up with all these sort of machines, drives, and energy generation solutions, but unless you can actually get that power securely to an end user, it doesn't matter. If you have a huge installed capacity of wind power, well, what are you going to do when the wind doesn't blow if people need power? What are you going to do when the wind blows lots and there's not actually that much demand? Do you just have to turn off your wind turbines, which happens, and is a huge waste? So how can we be smarter? How can we make better use of what's there? Is now what's driving change, particularly in places like the US and China. And the other thing to say about this is the swings are in, billions of dollars. So $10,000 million is the change over the last few years, which is large. So I think I've talked about this one already. I kind of was getting ahead of myself. It used to be that it was, over millions of years, fossil fuels get laid down. That fossil fuels we burn, heat up some water, and that turns a turbine. And we can open valves and change that whenever we want. Now we can't. Now the energy sources that we're increasingly relying on are variable. you can forecast them, you can't tell them what to produce, you can't schedule them in the same way. And to deal with that, we need demand side flexibility. Which demand side flexibility being the end user, the person who's consuming the power, or the companies or industries, or to actually respond to incentives and changes. And historically, that hasn't happened. If your electricity price, if you're contacted as an end user and saying, okay, we're increasing your unit price of electricity from 14 to 14.5, whatever it is, pence per kilowatt hour, you don't go, oh, well, I'll now start using this amount less electricity. You just grumble about it and get on with it. And that is a low price elasticity. You're not responding to price changes. And we really need that so that we can get that change in real time. Because if we're dealing with variability that even across days has this big fluctuation, sharp rises, the way to think about it is we need solar and wind to match that level, or we need end users to change their demand so that it flattens out those peaks, or the end users start matching and using their electricity in the way that matches up the availability of wind and solar. So that's how that's why the industry investment's moving towards networks. Okay, so what did Deloitte say about this? So they said sustainability is going to be a massive thing. Obviously, that's in so many places goals, that's in so many kind of governmental targets. Portfolio modernization. So that's rather than having these very big central generation, can you have distributed energy resources, all of the solar panels on people's houses, all the batteries in people's cars, all of the smart devices, and because of that, there's going to have to be a change in, rather than just here is your unit rate for electricity, or here is kind of what we're offering you. It's going to be more complicated. If you have smart heating, smart fridges, space cooling and heating, electric vehicles, etc., that capability all rolled into kind of an aggregated service that almost acts like a generation would be a massive benefit, this demand side management. Business model transformation, core growth. Building cleaner and smarter cities, there's going to have to be a lot of investment. We've sort of seen that already. And strategic planning, particularly at the utilities level. So if you've got a transformer at a grid supply point that connects the transmission system, those high voltage lines, down to those feeders, those lines that go out to individual houses and consumers, you've probably set it up to protect it, knowing that power flows in one direction. You've got a fairly predictable and consistent change in the amount of power needed at a particular time of day or season, and that's all changing. If you've got electric vehicles in there, if you've got photovoltaics, just because they're installed on people's houses, just take that demand out of the middle of the day, and you have this sort of dip in what a central system operator will see in terms of the demand. Okay, spending on digital technology has continued to rise. I think, given what I've said, that's fairly obvious now. The investment there is again in the hundreds of billions, and in smart grid infrastructure is increasing, although it's hard to see on this one. It's still networks and the actual power equipment that's dominating the investments. Battery storage, another one of exponential increase, huge factor. Electric vehicles is another huge factor. So what we're seeing is a big change in what a power system will need to look like. It's not that it's stuff that hasn't been seen before, it's just So it's not a step change. It's just it's a change that looks more like this exponential rather than this wasn't happening, it now is. So all of these things we've seen before, lots more power electronics. Well, power electronics have been parts of power systems for a long time. There's just a lot more of them now. Electric vehicles were originally proposed way back when cars were being developed for the first time, internal combustion engines, but they're massive. They're going to be massive, or they are. Lower inertia is a massive issue. So, and this is why I think this topic is so interesting. Society drives, normally, society drives engineering, engineering kind of drives society, and economics is and markets and industry trends are the thing that gives those signals to progress, for that loop to feed on itself. So I sort of wanted to tie this all up and split it into 3 pieces. In terms of generation, the challenge is around distributed. So you're not saying, okay, power flows from here, this one central or few central generators out. It's flowing back and forth in fairly unpredictable ways. It's non-synchronous, which means there's lower inertia on the system, which means the rate of change of frequency, that kind of 50 or 60 hertz oscillation, is going to be changing quicker than it would have if you had more inertia, if you had more synchronous generation. And it's non-schedulable. You can't dispatch it and tell it how much power to produce, which means that demand has to change. There's increasing demand, although there's actually decreasing demand in a lot of areas as well. There's a lot more storage. There's a lot more increased participation, demand side management, the electrification of transport, the electrification of heating, rural electrification, and distribution networks are turning into distribution systems. I'll talk about that more in a second. And at a system level, we're seeing more information, more data, which means that there needs to be more control. There's more options. There's more knobs to twiddle. Because we're seeing, digital substations, digital SCADA systems being used more broadly, that brings cybersecurity risk. It brings the increase of artificial intelligence or intelligent systems. We're also seeing more extreme weather, just globally, with places seemingly on fire for weeks and months at a time, but also very long cold spells, very and this is causing an increase, particularly as the systems get larger and we've got more complex systems, in thinking about the resilience of a system as a whole. How do we respond when there has been an extreme event, those low probability events? So lots of things going on, lots of challenges. One sort of specific that I was talking about was taking a distribution network where you've got on the left some generator, and it feeds through some transformer down 2 lines to, let's say, a load of houses. Well, if loads of people have got photovoltaics, solar panels, that power actually at some times of the day might flow backwards up through that transformer back into the rest of the system. What's that going to do to the voltages? What if actually there's electric vehicles and everyone plugs them in and charges them? Is there going to be a massive voltage drop? Can you fix that by joining the 2 ends of those feeders together? What does that do to the power flow? So all of these market trends, you can talk about at a high level, but really you need to know, all right, on bus 15, what is the power flowing through it and what is the voltage? Because if that ain't right, if that's not within limits, something's going to break. So the system still needs to work, despite kind of taking into account all the changes that are coming. And this is actually one of the slides from one of the pieces of coursework that we have for one of the units that looks at the smart grids. And so talking about that, and that's sort of the end of the piece on industry trends. This is the course more generally. So we have 8 taught units, each covering a different topic, lasting a fixed period of 10 weeks. 4 of those are entirely coursework based, so you'll be doing some project or combination of projects. 4 of those are exam based. Under normal circumstances, those exams are at a physical exam centre. We partner with a load of exam centres, normally the British Council, all around the world. At the moment, there's alternative assessments in place. They're still exam-based, but they're just done in a different way. Up to 4 of those units, those 8 units, can be taken each year, which means in 2 years, minimum, you'll have completed the taught component. And then there's the research component, a big 60-credit dissertation project that, well, I say normally takes a year to complete. 2 out of the last 3 students who are just graduating now managed to do it in 6 months, but that's the bare minimum. They were really working quite hard on it, and working on it as part of their job. It sort of complemented a work project and a research project that was on the same topic, which is why they completed it in 6 months, which is why I say a minimum of 2.5 years to complete. Most people take longer than that. But it's sort of up to you as you go through. You can, take 2 units 1 year, just if you've got big projects or a few holidays on. In terms of what the course actually looks like, for each course, you will get, to each taught unit, you'll get access to a space in our learning management system. It looks something like this. This one's split up into 6 taught components. And in those, you will have a video like the one on the left here. You'll have practice problems, some worked solutions, discussion activities. You'll get an academic tutor. So I'm an academic tutor for a number of the units, but there's other people as well. There's a whole host. We're lucky to be a very large power and energy division with a lot of expertise here. We have live video tutorials that happen every other week. There's kind of Q&A sessions. There's access to IEEE Explore, the number of textbooks online, and we send you a number of different bits of software so that you can work on sort of standard industry software as well. And it wouldn't be complete without a little bit of selling why this is the right place to go to. So Manchester University, the University of Manchester, has 25 Nobel Prize winners associated with it, who've either worked or studied here. 83% of our research was world leading or internationally excellent. The new ref is coming up, so I will update that when it comes out. But we are a fantastic research university, University of the Year for Graduate Employment, and one of the top 30 universities globally. And actually, the electrical energy and power systems group within that is one of the best, one of the real sort of showcases of that. So we have probably the longest running power system course in the world. We have many internationally renowned researchers. Actually, one of the researchers there is retired, but we have just as of a couple of weeks ago. But we have many academics who've real experts in their field, are editors of major journals, kind of have strong research collaborations, links with industry, patents, etc., etc. And the other major selling point is kind of all of you guys who are hopefully going to come on and join the course in February, coming from a number of different employers. So we have obviously people who work in transmission system, distribution system, and system operator, but we also have people who work in kind of engineering consultancies, the large sort of general engineering firms, sort of power generation companies, and a number of other industries as well. And there's some nice interactions you guys have with each other. To get onto the course, you need a 2-1 honours degree or equivalent in something relevantly technical like electrical engineering. We'll factor in industry experience. I do want to see a 2-1 level, whatever the international equivalent is, in power systems, maths, circuit analysis, the relevant units. I'll also look at the standing of the institution where you've studied. So how prestigious is it? How well respected is it internationally? There is if you very narrowly miss out, I can sort of factor in the industry experience a bit in a stronger way. But this is sort of the standard we're looking for. If you're not sure about it, Craig will kind of fill you in with the details, and if he's not sure, we can have a conversation, and we can answer your questions. We also need evidence of English language competency, and obviously you need to pay us the fees as well, but those can be split over in installments. The course is designed for 15 hours a week of study for 40 weeks a year. Able, one thing, to get back to normal, to attend the physical exam centres in what will probably be your local British Council, but we have a number of different groups. You need a computer that can be able to run the video conference tutorials, but if you're here watching this live, you certainly can do that piece. And you also need a PC that can run the bits of software we send you, such as IPSA, PowerWall, PSCAD, and MATLAB. And other than that, I think that's it. I hope to see you on the course soon. Please send me some questions and we can chat about them now, and I can hopefully answer them. And I will hand back over to Craig.
That's great. Thanks so much, James. Every time I hear the presentations like this, it fascinates me. And I did actually think of you the other day. I've just changed my car to an electric one. And so when I plug it in, I've now had to kind of time it where it's cheaper electricity, which turns out to be midnight to 5 a.m.
Yep.
with my provider.
We're going to see more and more of that.
Yeah.
Yeah.
So I couldn't wait to bring that up to you. When I first plugged it in through the day, and I was like, oh my goodness, it cost me a fortune. So I've learned a trick to do it moving. That's enough about me anyway. So yeah, as James said, please do get in touch with me if you have any questions around your suitability. Often we do get people sending through, or we would like you to send through your CV, your transcripts, and your degree certificate to me before you apply, so I can take a look at it. And as James said, if need be, I can share them with him, and he can offer me some guidance around, I guess, whether it's a suitable course for you and it's right for the pathway that you're looking to head down. Some people do choose to get in touch to ask questions around how to download the application form, what should they put in their personal statements. Again, this is stuff that I can support you with. There's my email address there, so you can reach me. And just a point to add, you may have looked on the website now and obviously attempted to download the application form. It's not actually live at the moment. It's just going through some changes to make it a smoother process. And my understanding is that it will become live again on I'm just bringing my calendar up now. So it will be available for you to access from Monday, the 26th of October. Is when it will be back on the course webpage. Okay, so that is my role, James. I'm just seeing if there's any questions come through from anybody. I do have one that somebody had sent me, but I can see Oliver has sent one through to you, James. I think you might have the questions open yourself. More geared towards the power systems rather than drives and machines.
Yeah, okay. A fairly specific question. So the question is, the course is more geared to power systems rather than machines and drives. It certainly is. We actually have a separate research group within the university that looks at machines and drives, and occasionally we'll kind of call on them for supervising some of the research projects. We just had one who's kind of looking at the interface between two systems, and it's quite machines and drivesy, so we ended up kind of calling on one of those. So nice within the university that we've got that, but this is, machines and drives isn't this course. We'll be covering the protection of these machines though. So we cover protection in a fairly general sense, and some of it will be applicable. There's certainly, when you're thinking about sort of zones of protection, there will be some that are around the drives and machines. And I don't know enough about protections of drives and machines to know what things we may or may not cover. If you're really interested in that, I'd suggest actually probably getting in touch with me, and I can forward the question on to one of the professors who looks into that. But yeah, I mean, we cover a lot of different types of protection, and it's fairly agnostic as to where they're applied. So there'll certainly be some things that are relevant.
Sure. I think Dean has sent through a question as well, James.
Yeah, can I do the modules sequentially? And so the modules are done. So you'll do a 10-week block, and then there's a little gap, and there's another 10-week block, and another little gap, and there's sometimes breaks in them for Christmas and Easter and things. Because they are 15 hours a week, I haven't yet let anyone do 2 of them at once. We tend not to run that many at the same time anyway. Just what we'll do is we'll group you into larger groups to study particular units. So you won't necessarily all be doing them in the same order. The first 2 units are all the core and the same, and they're the sort of the prerequisites for everything else. The final unit, which is, so I sort of look after the front end, the first and last one. The final unit is a group researchy project, and that one is done towards the end before the dissertation as well. So
yeah, I can actually share, if anybody is interested as well. James has put on the web page as well a kind of a table that's hyperlinked to the units themselves, so you can click onto them to do a bit more reading. I do get some questions sometimes, James, for me to send that out to people as well. So by all means, if anybody would like to see that in the interest of ease, do get in touch and I can share that table with you. You can click on the titles of each one to see each unit in more detail, as James was mentioning then.
yeah, and just looking now, I think if people have other questions now, it's probably right to just send you an email, and as I say, we can kind of follow up on that afterwards. If you kind of go, oh, I wish I'd asked this, just please get in touch. And if you're not sure whether what the equivalencies are, or whether the course criteria applies to you, or whether it's the right course, then either Craig or myself will be able to answer that. So yeah, send us an email, get in touch, and I hope to see you all joining us next February or for one of the intakes.
That's great. Thanks very much, James, and thanks everybody for joining us.